Okay. This next section is a section about exponential decay functions. In section 1, we talked about exponential growth functions. And let's just kind of quickly talk about some basics here. What I want to do is talk about either you have growth, okay, or you have decay. All right. And when you have growth, your function here, f of x equals a times b to the x. When you have a growth function, that means that your value b is greater than 1. Okay? And that's that base, okay, of your exponential function. When you have a decay function, what that means is that your decay, your base value, b, is going to be between 0 and 1. So b is a fraction. Okay? Now, to kind of make sure we understand what the difference is between growth and decay, growth means that the y values are going to get bigger. So the y values get bigger. Okay? And then decay functions means that y values get smaller. Okay? And so we'll go ahead and talk about how we get that and why that happens, okay? So when we have an exponential decay function, and let's just kind of talk about this, what we have happen is we kind of have the opposite effect of what we had before, okay? In an exponential growth function, our graph did this, okay? But in an exponential decay function, we get smaller and smaller and smaller as time goes on, okay? And the reason why is because when we take, 2 divided by 4, remember, exponential functions mean repeated multiplication. Okay, when you take this number and divide it by the previous one, you get a half. So each of these you're multiplying by a half, and that number is between 0 and 1. Okay, and so just so you kind of understand the idea here, if I take, say, 1/2 times 1/2 times 1/2, okay, when you multiply fractions, you just multiply across. So you get 1 times 1 times 1, which is 1 cubed, all right, over 2 times 2 times 2, which is 2 cubed, okay, which is going to end up giving you 1/8, okay? When you multiply with fractions, the numbers get a lot smaller, okay? So, and that's even if I take, and that's really when I take like 1/2 and raise it to the 3rd power, okay? That means I'm multiplying each of these 3 times, okay? So you multiply your numerators and then your denominator. When your denominator gets big, the number gets small, okay? So when the denominator is big, I'm going to write that down too. When the denominator is big, okay, the number is small, okay? And so when your denominator grows and gets really, really, really big, those y values are going to approach 0, and that's, what we call an exponential decay function, okay? So let's kind of look at just a kind of an example here. It says that Margaret has a bird feeder that holds 10 pounds of food. Okay, each day the birds and squirrels eat half the food. How many pounds of food will be left after 3 days? So what happens is on day 1, at day 0, okay, you've got 10 pounds of food. Okay, after 1 day, okay, you've got 5 pounds of food. Okay. On day 2, you have 2.5 pounds of food, okay? The question is, how do you get the 3rd day of food? Okay, and what you would do is you would take 2.5 and you would multiply it by a half, okay? So 2.5, and really what you're doing, when you multiply by a half, you're dividing by 2. So if you take 2.5 and divide it by 2, that's going to give you 1.25. Okay, so on day 3, there's 1.25 pounds of food, okay? And so if we were to write this out as an actual like function, okay, you know, when you think about it, what you're doing to these y values is that you're multiplying them by a half to get to the next one, okay? So your function, all right, your initial value, let me write this over here, the function here would be your initial value, which is 10, okay, on day 0, times your rate of change, okay, so you're multiplying each of these by a half, so you put 1/2 here, all right, and then you raise that to the x power, okay, and that's your function, all right, and that's how we get that. So, and so we just have this generic function here, okay. All right, so we've got, you know, this example here. We wrote out this example, kind of talked about how we get those numbers. You know, if you had, and the one thing I want to talk about real quick are these negative values and how, when you get these negative values, why you get such big numbers here. So over here on the side, if you've got room, what I want to do, I'm going to write out my function f of x equals 10 times 1/2 to the x power. Okay? Now, when I plug in -1 into this function, okay, that means that -1 is substituted in for my exponent. Now, what I do in order to evaluate this is I'm going to do 10 times, and when I have a fraction raised to an exponent, what that means is that I'm going to take 1 to the -1 power, all right, divided by 2 to the -1 power, all right? And so what ends up happening is I get 1 to the -1. When you have a negative exponent, remember what you do is that you just simply take this number, both of them, and you switch them, okay? So instead of 1 to the -1, over 2 to the -1, I'm going to write this as 2 to the first over 1 to the first. Okay, and when I take 2 to the first, I'm multiplying 2 by itself once, so I just really get 2 here, which gives me a value of 20. And that's what you get here when you plug in -1. Okay, let's do the same thing for -2 real quick, if you've got room. So if I've got f of x equals 10 times 1/2 to the x, and if I plug in -2, okay, with a negative exponent, what's going to happen is I've got 1/2 raised to the -2. I'm going to apply that exponent to each of those values in my numerator and denominator. So I get 1 to the -2 divided by 2 to the -2. All right, and then remember what I do to make those exponents positive. I just switch my numerators and denominators, and I get 10 times 2 squared over 1 squared. Okay, now 2 squared is just going to give me 4, so 10 times 4, and then 1 squared is 1. So 10 over 1 times 4 over 1 is going to give you 40. And that's why we get those values here, okay? So just kind of a trick when you're dealing with negative exponents. Okay, we've already kind of established that the value of b is between 0 and 1. Okay, the base represents the constant multiplicative rate of change. And you still have the same idea here as far as like domain and range goes. Okay, your domain is going to be all real numbers. You can plug in negative numbers here, you can plug in 0, and you can plug in positive numbers. But whenever you plug in a number into an exponential function like this, the range is going to be the same. The range is going to be all positive numbers greater than 0. You won't ever cross the x-axis with an exponential decay function. Okay, kind of like when you had an exponential growth function, it was just kind of flip-flopped. Okay, so that's the idea. All right, let's take a look here at this, and let's just kind of discuss what is happening here as far as this graph. Okay, our initial value. Okay, let's just take a look. Our initial value is the y value when x is 0. So when x is 0, the y value is 1. Okay? And now the issue is coming up with our base, and that's that multiplicative rate of change. And so what I want to do, what I notice is I'm going to take this y value here, which is 3/4, and divide it by 1, okay? And so when I do that, and let's kind of just look at that over here, and you can do any of these numbers. The easiest one is between 1 and 0, when x is 1 and x is 0, to take these y values and divide them. So if I take 3/4 and divide it by 1, it's just going to give me 3/4, okay? Now I could do the same thing. I could take like 9/16 and divide it by 3/4. Let's see what we get there. If I do 9/16 and divide that by 3/4, okay? First of all, this is kind of a hard problem because I don't know how to divide fractions. But I do know that dividing fractions is the same as multiplying by the reciprocal. So if I take 9/16 and multiply it by 4/3, then let's see what happens, okay? The 9 and the 3 divide out to 3/1. So this becomes 3/1. And then the 4 divided by 16 becomes 1/4. So therefore, what I end up getting is, I end up getting 3 times 1, 3 times 1 over 4 times 1, which gives me 3/4. Okay, and that's the trick, is dividing, so taking consecutive numbers and dividing them. Okay, I would get 3/4 if I divided 27/64 over 9/16. Okay, so this is my base. All right, this 3/4 is my base. And so what I'm going to do over here, base is 3/4. Okay, so my function rule is then going to be f of x is equal to 1 times the quantity 3/4 raised to the x power. And whenever you take a fraction and raise it to an exponent, you need to make sure you put parentheses around it, okay? Your domain of this function is going to be all real numbers, okay, from negative infinity to positive infinity. So I'm just going to write all reals, okay? My range is going to be my y values are going to be greater than 0, okay? It's not going to ever touch the x-axis. My horizontal asymptote is going to be the line y equals 0, okay? And that's the same thing as the x-axis, okay? That's the idea. All right, so let's go ahead and look down here and let's graph the exponential function, okay? Now, what I have, the easiest one to do is 0, okay? If I plug 0 into x of any exponential function, then I'm going to get a y value of 1, okay? So let's just kind of go through this, okay? But I know that this is going to be 1, all right? So my function, and let's write this out over here, f of x is equal to the quantity 2/5 to the x, okay? And the first one I want to plug in is -1. So f of -1, if I plug -1 in for x, then I'm going to get 2/5 raised to the -1 power, okay? To evaluate that, I take 2 to the -1 power divided by 5 to the -1 power. Okay, to make those positive, what I do is I switch them around. And that's just going to end up giving me 5 to the first over 2 to the first, which gives me a value of 5/2 or 2.5. Okay, so let me write that in over here, that this is 5/2 or 2.5. Okay, so at -1, okay, at -1, my y value is 2.5. So I'm going to come up here and I'm going to plot this point right here. All right? So at -1, I have a y value of 2.5. All right, if I plug in 0 into this function, and let's go ahead and do that over here. If I do f of 0, all right, then that means I'm taking 2/5 and raising it to the 0 power. Anything raised to the 0 power is 1, okay? That's a given. So over here, I'm going to write 0, 1, okay? Now the next thing I'm going to do is I'm going to plug in 1, all right? And so if I do f of 1, okay, f of 1 is 2/5 raised to the first power. And anything raised to the first power is just going to be itself, Okay, I'm taking 2/5, multiplying it by itself once, okay, which means I'm just going to get 2/5. Okay, and 2/5 as a number, as a decimal, is going to be 0.4. All right, so I'm going to take that. At 1, this is going to be 2/5, or it's 0.4. Okay, so at 1, we're going to get 0.4 right about here. Okay, and then let's plug in 2 into this function. All right, and so I'm going to do f of 2, and that's going to give me 2/5 squared. All right, so if I take that and raise it to the 2 power, then that means I'm taking 2 squared divided by 5 squared. And so we get 4/25. All right, and this number as a decimal is not as apparent as others. Let me plug that in the calculator and see what we get. All right, so then what we end up getting for here, this is a value of 0.16. Okay, so what we can notice here is that as x gets bigger, all right, and hold on, this was 4/25? Yep. Okay, or 0.16 as a decimal. So 2, and that's going to be way down here. All right, and what we notice is that these numbers, as x gets bigger, the y values are getting much smaller. All right, and that's all algebra is, guys. You know, what we're talking about is these, these relationships between x and y. All right, and that's all we're looking for. And I want you guys, and I want you to see something here. Okay, when I have this base here of 2/5, okay, and if I start raising this to an exponent, what's going to happen is you have 2 squared, which that number, is going to get bigger. Okay, 2 squared is going to give you 4, but if you take 5 and raise it to an exponent, your denominator is going to get much bigger, much faster. Okay, let's just do f of 3 just to see what we get. Okay, that means I'm going to take 2/5 and cube it, which means I'm going to take 2 cubed divided by 5 cubed. All right, now 2 cubed, 2 times 2 times 2 is going to give you a value of 8. If I take 5 cubed, it's going to give me a value of 125. Okay, so notice the difference between this number and this number. Okay, a base of 2, 2 squared versus 2 cubed, you go from 4 to 8. Okay, not that much of a change. But when you go from 25 to 125, you can see that the denominator is getting much bigger. Okay, when the denominator gets bigger, your number gets smaller. All right, that's the first page. Let's go to the next page. Sorry it's taking me so long to get through this, but there's just a lot of information. Okay, comparing exponential growth and exponential decay functions. We've already kind of talked about this. When your base is a number that's larger than 1, okay, you're going to get an exponential growth function. So as x increases, your y values increase. Okay, when you have an exponential decay function, that means that your base is between 0 and 1, which means that as x gets bigger, your y values get smaller. All right. Now we also can write this a couple of different ways. Okay, it's kind of interesting, but if I write this function as f of x equals 2 to the negative x, that's the same thing as me raising that to the, having a base of 1/2 and raising it to the x power, okay? Now, here's the reason why, okay? If I were to take this function, f of x is equal to the base 2 to a negative x power, all right? When I write that, okay, I'm really writing this as 2 over 1 to the negative x, okay? And when I have a fraction raised to an exponent, I can apply that exponent to the numerator and the denominator. So what I end up getting is I get this. I get 2 to the negative x over 1, okay? And I could write this We just write it as raise that to the negative x as well. It doesn't really matter because it's 1. If your base is 1, it's just going to stay at 1. Okay, 1 times itself, however many times, is always going to be 1. Okay, but anyway, what we want to do is we're going to switch these, okay, to make our exponent not negative, because it's not proper to write things with negative exponents. Then I write this as 1 to the x over 2 to the x. To switch them, I move them from the numerator to the denominator and vice versa. Okay, and then I kind of do this reverse step where I take this value, okay, 1 to the x over 2 to the x. If I have a numerator and denominator raised to the same power, then I can write this as 1/2 all raised to the x power. And all I'm doing is taking this, turning it into a fraction, raising everything to the exponent, then realizing I have a negative exponent, making them positive, and then going back and writing that whole number raised to a single exponent. So these two things are the same. Okay? Now, I don't really expect you guys to necessarily, I hope you understand my logic of going through this, but I need you to remember that something raised to a negative exponent is the same thing as taking the fraction of that base and raising it to a positive exponent. Okay? So either way, it'll give you the same value. So, I mean, they mean the same thing. And that's why for any x value, okay, this is a column of x values. These are the y values of these functions. Notice how you get the same thing for each of those values. Okay, and that's that. All right, let's talk about graphing an exponential function. So what I want to do is I want to consider this function f of x equals 5 to the negative x power. Now what we just figured out was that if I have 5 raised to the negative x power, that's the same thing as me writing f of x is equal to 1/5 raised to the positive x power. And that tells me that if I have a fractional base, that this is going to be an exponential decay function, okay? And we've kind of written that all out over here as well, okay? And we've kind of already just got the y values just written there. All right, so what I want to do is I want to talk about the initial value. So when x is 0, what's the y value? Okay, and we can tell by the table that this is going to be 1. Okay, the base of this function is the number that's raised to a power. All right, so this is going to be 1/5. All right, we don't want to write 5 over here because we have a negative exponent. All right. Okay, my domain is true for all exponential functions. It's going to be all real numbers. Okay, and then notice that all of my y values here are positive. Okay, so my range is going to be y is greater than 0. Okay, my horizontal asymptote is y equals 0, which is the x-axis. Okay, and then what we can just do is we can graph these and plot these points. So at -2, okay, on the x, it gives us a y value of 25. So -2, 25 goes, oh dear, okay, 4, 8, so these go up by 2, so 2, 4, okay, so this is 24, this is 26. So 25 is over here in between these two. Okay. If I plug in -1, that's going to give me 5. So it's going to be this point right here. Okay. If I plug in 0, I'm going to get 1. Okay, if I plug in 1, I get 1/5. And then 2, we get pretty darn close to the x-axis. So connect those with an exponential curve. And that's what we're looking for. Okay, and that's that graph. So not too bad. Okay. All right, the other thing we want to do is be able to simplify the exponential functions to determine if we have an exponential growth or decay function. So let's go over here first. Now, what I notice is that we're raising this to a negative exponent. Homie, don't play that game. Okay? So what I end up getting, what I have to do is turn this into something with a positive exponent. So what I need to do is simplify this. All right, so f of x is equal to 3. And then because I'm raising a fraction to an exponent, I raise the numerator to that exponent and the denominator to that same exponent, okay? Now what I do is I take this and I switch my numerator and denominator to make the exponents positive, all right? So we get 3 times, and this is going to be 4 to the x over 3 to the x, all right? And then I do, now since I have a fraction that's raised to the same exponent, I can take that exponent out and raise it to the whole fraction. So I get 3 parentheses 4 thirds quantity to the x power, okay? And I've rewritten this with a positive exponent, okay? So then what I know is that my base, 4 thirds, is larger than 1. This means that we have a growth function, exponential growth, because my base is larger than 1. It can be a fraction. 4 thirds is a fraction, but that value of the number is larger than 1. Okay, so we have a growth. Okay, the next one, okay, this is going to be a decay. Just watch. All right, so same thing. F of x is going to equal 1/10 times 5 to the negative x power over 4 to the negative x power, all right? And so then f of x is going to equal 1/10. Because these are negative exponents, I'm going to switch them, all right? Bring them from my numerator to denominator and vice versa. So this is going to give me 4 to the x power divided by 5 to the x power, all right? And so then I get 1/10 divided by, okay, I'm going to do 4/5, and this whole thing is raised to the x. Now, 4/5, this number is less than 1, but also greater than 0. Therefore, because of that, we have a decay function, all right? And that's how we can tell. So we do need to understand this process. It's very important that, you know, if you get to a point where you don't know how to simplify your exponents, go back and watch this section of the video, okay? All right, let's do one more problem, okay? And this is a real-world exponential decay function. And it says a certain multivitamin is absorbed at a constant rate of 15% each hour. What function would model this scenario? How much of a 100 milligram dose is left to absorb after 3 hours? So here's what we've got, all right? All right, so this problem's a little bit weird because the numbers don't necessarily exactly tell you exactly what to do. So what happens is a certain multivitamin is absorbed at a constant rate of 15% each hour, all right? So that's a little bit different, okay? And the reason we have to kind of think about, you know, what would happen here is this. All right, if we start out at time 0, all right, let's just think of a table here, all right. Let's just say that at time 0, you have 100% of your vitamin, okay. What happens is this is being absorbed at a rate of 15% each hour. So after 1 hour, how much of that 100% of the vitamin is left over? If you take away 15% of it, you're left with 85. So to get your multiplicative rate of change, you take 85 and divide it by 100, which gives you 0.85. Okay, this is your base. Okay? And you have to think about it like that. You can't just automatically assume that it's going to be 15%. You have to think about what is happening here, okay? And so then, all right, you know, how much of a 100 milligram dose is left to absorb after 3 hours? So if I write my function here, f of x is equal to 100 times 0.85 cubed, okay, or I'm sorry, x, okay, this is my general function for this scenario. Okay, this answers the first question, okay? And the initial value is 100 milligram dose, okay? That's what you're putting in your body. Your body absorbs 15% of it each hour, okay? So but that's what you take away, all right? So you have to think about what you're left with, all right? Okay, so let's plug in 3 into this. F of 3 is equal to 100 times 0.85 cubed, all right? So if we plug that into the calculator, we're going to take 0.85 times itself 3 times, so 0.85 times 0.85 times 0.85, and then I'm going to multiply that number by 100, and that's going to give me 61.412 milligrams is left in the body after 3 hours, okay? So, you know, exponents are used a lot in medicine. They're used a lot in, you know, in various different things. So it is important that we know that, know how to do it. So, because they will kind of keep popping up later and later into your other curriculums, okay? Hope you enjoyed this video. Talk to you soon.